All right, so if you didn't see this announcement earlier, I wanted to point it out. Our IAA Tharva is going to have online office hours instead of being in class, since there's relatively few of us here. I can generally get around to you all here. So he's going to have online office hours. Tried to pick some hours that fit in his schedule and were in gaps during the other Pathways tutoring, so that if Pathways tutoring wasn't open, maybe a Tharva was available. So in any case, we've got 4 days per week he's going to be doing this. Let's see if I can make this bigger. Monday and Wednesday afternoons, 3:30 to 4:30. Thursday, 2 to 3, and then Friday in the morning before. I think that 10 to 12 is before the Pathways Tutoring Center opens on Friday morning. So I think it opens at noon that day. Let's see. There's some instructor that changed their hours slightly, and I don't know what's different about this, but they said, oh, we've updated one instructor's hours. So here's the current Pathways hours updated as of yesterday. Like I said, I didn't really compare to see what was different, but it didn't look much different. But in any case, yeah, so a Tharva is on Friday between the 2 times in the morning when this is open already, so 10 to 12, and hit some other kind of gaps here and there also as best he could during his availability, which is like 5 hours a week. So in any case, just another opportunity for assistance, tutoring, homework, help, whatever it is that you need. Let's see, so just rundown of stuff coming up in the near future. Today, I want to finish up with logarithms. We're going to do a few things, talk about some properties of logarithms, and then how to both use them to help solve exponential equations. Since logarithms are a different way to express exponents, they can help us solve equations where exponents are unknowns. And then we're also going to, later this week, we're going to be talking about, let's see, what is it? General, let's see, quadratics and something else. I forget what all is in 5.3 and 5.4 precisely. But about quadratic functions, and there's something else there, maybe rational functions. But just the next chapter includes like 12 different semi-related topics. Chapter 5 does, so we're just going to talk a little bit about all of those on Thursday in class to get you started for what we're going to do when we come back. So 5.3 is about quadratic functions, parabolas in graphical form. Just a few facts about them. You've probably seen all of it before, so that's why we're kind of just jumping in and doing a little bit on Thursday, and then you'll have the lessons due on Friday, and then the homework due after break in case you need more time on that, but it's relatively short. But homework up through 5.4 is listed through now, and just keeping in mind, it seems like it's a long way off, but there's spring break in between now and then. End of March, exam 2 is going to be in class on Thursday the 24th. So that's like 3.5 weeks from now, but one of those weeks you're not going to be here, we're not going to be here. So not too much more on that. It actually covers chapters 5 and 6, but we're finishing up chapter 5 right after break. That's really kind of the end of it. And then 6 is like just a couple small topics that we're covering between the end of this next week and then the 22nd there. So, in any case, let's see. What other things did I want to mention? Start of class stuff. Oop, did not mean to make that shrink. So, what I want to talk about then, I can't think of anything else. I was thinking I had another announcement. I don't think I do. So what I want to talk about now then is just some, let's take a look at actually the end of the 4.8 homework, just for a moment, not to do this right now, but just to look at what I'm talking about. So the last couple of questions in this are not something we've talked about. The beginning part is convert this into log form or use some log properties, which we're going to talk about today, but those are pretty straightforward. Like there's a list of properties, you just follow the instructions. But what we're going to be able to do by the end of what we're talking about with logarithms is, here's the equations, solve some strange things that look like these. Some of these are stranger looking than others. But maybe you can see, based on how logarithms are related to exponential expressions, this question number 15, no, your numbers may be slightly different in this, but it says log without a base written. That means common log or log base 10 in this class. So I say, oh, log base 10 of this linear expression equals 7. If I were to just rewrite that into exponential form, it'd be 10 to the 7th equals the stuff inside the parentheses, right? And at that point, although 10 to the 7th is a huge number, it's just, what is that? 1 with 7 zeros, so 10 million? So 5x plus 160 equals 10 million. A big number involved, but not very hard to solve, just to subtract and divide once you get it out of logarithm form. On the other hand, something that looks like b, there are 2 logarithms there across from a single number, so I can't do the same sort of conversion when I have these 2 separate logarithms. They're both log base 3, but we haven't talked about how to subtract logarithms yet. And that's a little bit weird. So it seems like, well, I should be able to do something with them because they're both log base. Just like if you have 3 to a power and 3 to another power, you should be able to do some stuff with them, whether it's multiply or add or something. So these should somehow be combinable at least a little bit. But in order to figure out how to combine them so it could look more like the part A question, we have to think about what logarithms are. And remember that a whole logarithm expression, something like this log base 10 of 5x plus 160, it's equal to 7. So that means that this whole expression here represents the same thing as a number 7 does. And 7, when we rewrote that, was the exponent. So a logarithm expression like this, whether it has a written base or not a written base, log base 10 in this case, of 5x plus 160, that's representing an exponent by telling us what that exponent does to what. So it tells us, well, it turns a 10 into a 5x plus 160. Okay, what is it? Well, it's 7. It's kind of weird because it's not numerical, so it's not something you would know by looking at the log expression on its own. This is an equation to solve for x. But this expression here means that this whole log expression is equal to 7. And 7, written in a different form, is an exponent. So this is some sort of exponent. It's the exponent that turns a 3 into an x plus 1. Well, I don't know what x is, so I can't tell you what that exponent is. And this is the exponent that turns a 3 into a 27. Well, in reality, I know what that is. This is really just the number 3. But if I knew how to write this one, and I knew how to write this one, if I were doing subtraction, I'd be subtracting 2 exponents, 2 things that represent exponents. And thinking about like subtracting exponents, it's not a frequent thing that we do, but you can subtract exponents if you have expressions with the same base in a couple of different places. I'm just going to jot this on the board. Like, let's say I had something like x minus 9 to the 5th power over x minus 9 squared. I can simplify this without having to do any distribution or FOIL of x minus 9, right? Because I have an expression of the 5th power divided by an expression of the 2nd power. I can simplify it by using a property of exponents that says I subtract those exponents, right? So I do x minus 9 to the 5 minus 2 power, otherwise known as 3rd power, right? So I can subtract exponents in certain cases if I have something where I've got the same base raised to 2 different powers that are being divided. So division of whole expressions that have the same, like, I wouldn't call it exactly like terms, but it's the sort of similar expressions. You've got pieces that are the same. If you've got expressions with exponents where the bases of the exponents are the same, you can simplify by, well, subtracting the exponents if they're divided like this. You add the exponents if it was multiplication, right? If I had something more like 2x plus 1 to the 6th power times 2x plus 1 to the 8th power. I could say that's 2x plus 1 to the 14th power, 6 plus 8. I don't have to multiply that out, but I can, instead of having this longer expression, I can consolidate it by reducing the repetition of writing this, because exponents represent already repeated multiplication. This is 6 factors of 2x plus 1 multiplied on by 8 more factors of 2x plus 1, so there's a total of 14 of them. So exponent properties, when we actually see the numbers written as exponents, say, oh, add the exponents or subtract the exponents. When I've got the exponents expressed as logarithms like this, I have one logarithm minus another logarithm. Another way to think about combining this, and this is not something that you actually have to do in this problem because log base 3 of 27 is just the number 3. We could actually make it look more like the previous question. But let's say this was a 40 or something instead of a 27. Well, if I'm subtracting 2 exponents, the whole expression's values must actually be being divided. So the expression with the expression with the exponent being divided, I end up keeping that same expression with subtracted exponents. In logarithm form, and like I was saying, so this is a 4.8 homework before the log properties are discussed, but this expression here with 2 logarithms being subtracted, I'm just going to use this bar here to write something. It's not the answer to this question, but log base 3 of the quotient of these two things, x plus 1, is the result of having used this exponent, whatever it all is, on a number 3. So if I were to take x plus 1 and divide it by 27, no, so in reality this is not what this line was for. This would be a way to rewrite, oops, and it didn't want an equation in that. If I wrote equals 2, that would be a way to rewrite that previous equation, because the previous equation said I have 2 exponents subtracted, the exponent that turns a 3 into an x plus 1 and the exponent that turns a 3 into a 27. So if instead I think about the exponent that turns a 3 into an x plus 1 over 27, the quotient of those two things, the quotient of these two, I'd be subtracting, that's the same as subtracting the 2 exponents. And the result of subtracting the 2 exponents was 2. So this expression here is still equal to 2. Now, does that help us in this case? Well, if I wrote it in this form, let me pull up a blank document. That's not blank. We're going to take a look at that later. That's just messier expressions. Let's see. There we go. If I were to be looking at log base 3 of x plus 1 over 27 equals 2 in reality, which is what this was. Trying to solve that, I should be able to write, if this is a 2 here, it just won't let me write that in this Math AS bar because it wasn't expecting an equation. I'd write 3 squared equals that stuff in parentheses, right? So let's see, 3 squared. I'm going to reuse the equation editor. I hate it on here, but it'll work. Three squared. This will be much easier to understand what on earth this expression is about. It was what, x plus 1 over 27? Yeah. X plus 1 over 27. Apologize, I couldn't see the, so this equal to a 2 where it says undefined. Rewriting into exponent form is 3 squared equals that fraction. And from here, although this isn't a particularly nice equation to solve, I should be able to solve it, right? I could square the 3, that's obviously 9. I could multiply both sides of this equation by 27, so I don't have a weird fraction. And then I would just have 9 times 27, whatever that is, 243, equals x plus 1. So at that point, it's 242. So log properties allow us to consolidate added and subtracted logarithms. And it seems like, it's a strange property, but it's just related to exponent properties. Let's see. This is just the textbook from Module 4. Later on in it, let's see, starting page 45, there's a section called Properties of Logarithms. And it goes through a whole description. If you read it, it can maybe help you think through why these properties work. They're fairly easy to just remember, but also easy to get confused when you're in the middle of a test. So it helps if you can think your way through why they make sense or how they're related to other properties that are stuck in your brain better from more years of use. But this is the multiplication version of what we were just talking about. Remember that x squared times x cubed equals x to the 5th. That's like this. If I'm multiplying together a whole bunch of factors of x, I can represent that with exponents on x's. But some of it's written out as multiplication. So x squared and 3 more x's multiplied on, x cubed multiplied to make x to the 5th. We add the exponents to do that. And we can do that because they have a common base. If it's x squared times y cubed, there's nothing we could really do to make a single expression out of that, because we've got some x's and we've got some y's. I could say it's xy quantity squared times an extra y, or something, but it's not going to quite condense the same way. So looking at the expression log base 2 of 4 times 8, that should be the same as log base 2 of 32. It is, right? 4 times 8 is 32. But if you wanted to, and if you're thinking like 2, that's a 2 and 32. I know 32 is some number of 2's multiplied together. How many? It's a lot. But I also know 32 is 4 times 8. 2 squared makes 4. 2 cubed makes 8. 2 to the 4 times 8, 2 to the something to make 4 times 8. It's 2 powers of 2 and then 3 more powers of 2, just like the last one with x's. So the value of this is the exponent that it takes to turn a 2 into a 32. But that's the same as the exponent it takes to turn a 2 into a 4 and to turn a 2 into an 8 added together. Because that's what we'd be doing if I were writing out, 2 squared times 2 cubed is 32. The squared and the cubed, second power and third power, make that 5. It's adding those exponents if you want to think about each logarithm as an exponent in this expression. This is the exponent to turn a 2 into a 4, an exponent to turn a 2 into an 8. That's the 2 plus 3. That's the same as 5. The exponent to go maybe directly from, base of 2 to a value of 32 takes an exponent of 5, which is 2, 4, 8, 16, 32. It's not a huge number, but you can split down numbers like this to validate that you're using the log properties correctly, that it should be adding logarithms if you would have been adding exponents to get the result inside. So this works whether or not these are numbers that I know, or whatever the logarithm base it is. Doesn't have to be 2 for sure, it can be any base. The property in general says that log base b, whatever base you want it to be, of 2 things multiplied together, whatever those 2 things are, whether or not they are factors, like, not factors, but I'm looking, multiples, like squared, cubed, 4th power of b, whatever they are, they don't have to be any special numbers, other than we want them to be positives. We're just going to use positive numbers around logarithms. if I have a positive base, I can't turn it into a negative number with exponents, so that's part of the reason. And if I have a negative base, it only has values every so often for specific numbers. So we're just going to be using positive bases on exponents and positive input to the logarithm, stuff inside the parentheses, the argument of the logarithm. But doing that, we can get values for that are positive, negatives, fractions, anything, as the value of the whole log expression. It can come out any way. But in any case, if I have a logarithm of a product, I can rewrite that as a sum of two logarithms, or vice versa. If I have a sum of two logarithms that have the same base, I can combine those to write it as a single logarithm of a product of what was originally the two separate arguments. Multiply the inside parts together, which are like the result of having used the exponent, the 8 and the 4 or the 32. So in any case, I did just want to point out here, you can use these properties in either direction. Some books will say, expand this logarithm by using properties, or condense this logarithm, or consolidate these logarithms. Just do whatever makes something easier. Sometimes taking a logarithm and breaking it down into its component parts, more parts, but each one a little bit simpler argument, is useful. If you're solving an equation that has multiple logarithms in it, usually it's easier if you take them all and combine them into one, if you can do that. All right, so log property 2 is the subtraction and division corresponding piece to that. So multiplication and addition are related via exponents. If we're multiplying, we add exponents. If we have logarithms that are added, we must have multiplied the inside parts, their arguments. Similarly, I'm not going to go through the whole thought process again on that, but it's the same as what we were talking about with these. If I have a logarithm of a quotient, then I can split that into a couple of different logarithms that are subtracted and have the same base. Or, to use this the other way around, if I have a couple of logarithms with the same base and they're subtracted from one another, I can consolidate those together or combine them together into a single logarithm where I'm dividing the two arguments or inputs to the logarithms. And again, this comes from the idea that logarithms are exponents. And when would I be subtracting exponents? Oh, if I were doing a division of two expressions that have the same base, two exponential expressions with the same base. These aren't written in their exponential form. These are the values of those. But if I'm dividing them, then I know that I could subtract the individual exponents that give me m and n to get the exponent that would give me the simplified m over n. Subtract the exponents. Subtract the logarithms. So just as a note, if you have a logarithm with subtraction inside the parentheses, there's nothing you can do to separate that out. Or if there's addition inside the parentheses of a log expression, that's not something that's helpful or useful to change into a different form. It's logarithm of a product or quotient that you can split into addition or subtraction of separate logarithms. All right, so this third property here is related to another exponent property, and it's just a variation on a theme, in reality, of the first log property. First log property said if I had, first one in this list, if I have a logarithm of a product of a couple of things, I can split it into a sum of the logarithms of those two items separately, or vice versa. Log property 3 says if I have a log of an expression that's raised to a power. Now, m to the c power could really be just written as m times m times m times m, however many times c is. I don't know what c is. In fact, it doesn't even have to be a whole number. It could be any sort of number. But if that was m cubed here, log base b of m cubed is the same as m times m times m. So according to the first property, used repeatedly, I could say that's log base b of m plus log base b of m plus log base b of m. 3 times added together, otherwise known as 3 times log base b of m. If you add something 3 times, you could shorten that up and say 3 times whatever it is you had been previously adding. So similarly, for any power, and in fact, even if it's not a whole number power, not something I could just write out as a repeated factor, if I have a logarithm of an expression that's raised to a power, then I can rewrite that as a logarithm of that expression to the first power, just plain old base of the exponent that had been inside, and say it's repeated c times or added together c times by writing this as a coefficient. So this is really just a special case of, in the case of whole number exponents, it's a special case of our first log property, but actually in reality it applies to all. This is useful also in solving equations. But if you can imagine, if I had log base 2 of 5 cubed, like, all right, log base 2 of 5 cubed, if I were writing that out and trying to figure out what that value is, log base 2 of 5 cubed. Well, I could either think that's 125. 2 to what power is near 125? And kind of count it up. Let's see. 2, 4, 8, 16, 32, 64, 128 is a little bit too big. So a little bit less than 7, right? It's like 6.8, 6.9 maybe. Just by kind of guessing, right? 5 cubed is 125. 2 to the 7th is 128. That's pretty darn close. Now, on the other hand, according to this log property, this should be the same as 3 times log base 2 of 5. Now, log base 2 of 5 is maybe harder to estimate. Log base 2 of 4 would be 2. So this number is a little bit larger than 2, but this being between 4 and 8, that's a lot smaller gap than what we're dealing with when we're in the 120s in powers of 2. So this is somewhere between 2 and 3, and then I multiply by 3. So something that's between 2 and 3, not subtraction, but something between the whole number values of 2 and 3, if I triple it, is going to come out somewhere between 6 and 9. It may be hard to see that that's the same thing here, but it should seem reasonable that this would be the exponent to turn a 2 into a 5, added together 3 times, would be the exponent that turns into a 5 times 5 times 5. Because whatever that number is, the exponent to turn a 2 into a 5 times 5 times 5 would be a 2 to a something, 2 to a something, and 2 to a something, makes 125. Should still match up with this. It's just not easy to estimate these numbers. And part of what I do want to talk about today is how on earth do you get values for solving equations when I don't know things like that? How do we get that off of a calculator if I want a decimal value instead of just eyeballing it somewhere between 6 and 7? Graphs, or there's log buttons on your calculator that we can use in specific ways to get the answers we want. But in any case, this log property 3 allows us to write expressions with exponents instead of having a logarithm expression with a factor in the front, or vice versa. One or the other might be useful in helping to solve an equation. So there's a whole bunch of examples here using these properties of logarithms. So if these don't seem familiar or if they get confusing, take a look at these examples that are just here. This is page, I don't know where my page header went. I zoomed out too far. There we go. Page 48 or so in the module 4 text. There's a video where they talk about it a little more. There's a bunch of examples here like log base 2 of xy, the product. I can separate out into an x and a y logarithms, base 2 of those two things added. This expression here, if you want to, solve for x, like, oh, if you rewrite it, x squared is 121. I did want to point out something about log equations. When we were talking about logarithms, we're going to have positive bases and positive arguments, stuff inside the parentheses. So if you're solving an equation by taking it out of logarithm form like this, x squared is 121. You might get extra answers that don't check when you go back to the original equation or don't work out. Those are called extraneous solutions. There's a solution, there are two solutions to x squared equals 121, right? Plus and minus 11. But I can't have negative 11 as the base of a logarithm, so the answer to this equation, which started out with other things in it that we eliminated by rewriting it, does not have a solution of negative 11, only positive 11, which seems weird, but we just don't allow in expressions logarithms to be written with negative bases. So we'll exclude that, not because it's not a square root of 121, but because the original expression here, the x was the base of a logarithm. Kind of like you might have done this with solving fractional equations before, and maybe a number you get as an answer would make the denominator in the original 0, but through the process of solving you got rid of the denominator, so it looked perfectly fine in later steps, but go back to the original and it doesn't work, it doesn't make sense for that one anymore. It's the same idea, so just make sure that you don't end up with a value by rewriting that would make either the base of the logarithm or the input, the argument to the logarithm, anything negative. It's not negative numbers for x always that are the problem, it depends on what all else is around. But something like this. This has multiplication and division, 2a over 3, 2 times a divided by 3. I can split that into 3 logarithms, a logarithm of a 2 and an a and a 3, in various phases of multiplied and divided. So in this expression, there's a 2 and an a that are multiplied together and a 3 that's divided by. So I can write this as a log of a 2 and a log of an a. This is base b, generic base. So log base b of 2 and log base b of a that are added together, and then a log base b of 3 subtracted from all that. Now just, again, kind of as a, how this is all related to exponent properties and if this helps. 2a over 3 would be the same as 2 times a times 3 to the negative 1 power, that 3 in the denominator. You see that done less when it's numerical denominators, but if you remember having all these expressions with x and y and some in the denominator, and you could rewrite with negative exponents, this is the same as the argument to the logarithm. If you wrote it like this, say, oh, it's all multiplication now, so it should be all adding. Yep, log base b of 2 plus log base b of a plus log base b of 3 to the negative 1 power. Which, if you wanted to, this exponent could be written as a coefficient instead, a negative 1 coefficient. So rewriting something with negative exponents, you could change any division into addition, which doesn't actually change your answer. It's like, well, if I did it that way, I'd get it wrong. This is the same as negative 1, which we don't normally write the 1, just a negative, log base b of 3. And if you can see, negative 1 log base b of 3 would be the same as the last term here that's written as a subtraction. If I were to add a negative 1 log base b of 3, that's the same as subtracting log base b of 3. So you can rewrite expressions that are all multiplication and division as all multiplication, or visualize it as multiplication even if you're not writing it down. So something messy like this part E, like, oh my gosh, that looks awful. if you think of it as all multiplication, I've got a 4 and an x squared and a y and a 3 to the negative 1 and a z to the negative 1/2. That's 5 things multiplied together. Some have exponents, some are negative exponents. But you can see this final answer is 1, 2, 3, 4, 5 terms. The arguments of the logarithms are a 4, an x with this 2 that used to be an x squared, 2 written as a coefficient instead of a power on x. Here's our y. Here's our 3 from the denominator, negative log base b of 3, just like this one. And then this z from the denominator, minus 1/2 log base b of z. So instead of having exponents, if we want to, I mean, I could write this as 5 pieces like this without any coefficients and have like the 2 on the x as an x squared instead of a 2 coefficient on log base b of x. There's a lot of different ways to rewrite these equivalently. And one isn't like, this is the best way to write it and this is bad way to write it. There's just a lot of different ways to write the same thing. Some are maybe easier to use in certain situations for solving equations. Some are maybe easier to understand if you're looking for something in particular. As long as you can recognize that it's equivalent or write something in a slightly different way, you can figure out, if you're trying to solve something, what is going to help you the most. There's not like only one answer for how do you write this. Just like lots of math things, there's lots of equivalent ways to write expressions, and how you write it isn't the important part. It's important that you understand how it came from something else or how to rearrange it if it's not helping you the way that it is. All right, so in terms of solving, here's the story of the history of logarithms and some money stuff. But I just wanted to point out something like this expression here. Now this was an example using compound interest. We're not going to focus on compound interest. It was just, let's say I have this equation. We started with $2,000. It was growing at a certain rate. We were getting interest 4 times a year. You know, the 4-unit growth factor, 4-unit growth factor would be what we have here, 1 plus 0.06 over 4 to the 4t, times 2,000 gives us 2,500. It's like asking us, how long does it take, how many years does it take to turn my $2,000 into 2,500 just on this minimal amount of interest? It's going to take a long time. But if I wanted to solve it, at a certain point I say, well, I could work out this growth factor a little bit more if I wanted to. And from there, in terms of solving, maybe instead of having 2 different coefficient type numbers, like whole numbers, nothing with unknowns, I could divide them. So I have 5/4 is 1.015 to the 4t. But at that point, algebra steps wise, we're kind of stuck. So if I were to rewrite this into logarithm form, I could write an answer, but nobody, if you ask them, how long will it take me to get $2,500? They don't want an answer, oh, log base 1.015 of something years. Somebody wants like a decimal number for a number of years out of that. So I want to talk about how to get a numerical decimal approximation answer to this using a calculator. Because yes, we could find an exact answer to this by just writing log base 1.015 of 5/4 equals 4t, right? And then to get t, you can divide that by 4. But how would you evaluate that? To get an estimate or to get an approximation to the value of that. So let me just rewrite this here. I could rearrange this and get the t by itself. We have the skills, we've done this before. Log base this of that equals 4t. So if I knew what that value was, I'd divide by 4, and I'd have t. But how do I get a number for that? Two ways. One is a fourth log property. Probably the least useful of the log properties, other than if you come across an expression like this. But another, not a property as in something to do, but just as something to know about logs, something that you can do with logarithms, because every logarithm only has one, a logarithm with a single base only has one value all the time. They're functions. If they have one set of combination of number down below and number up above, you get the same result all the time. Or if I were to tell you that I knew the value for log of 5/4, and I'm writing log, just log base 10, common log. If I told you I know the value for this, it's going to be a single number. What power of 10 turns it into a 5/4? I don't know what it is. But if I told, it has one value, right? 5/4 is equal to this thing, according to this equation. So if 5/4 and 1.015 to the 4t power are equal, then so are their logarithms base 10, or their logarithms base e, or their logarithms base 17. Because to turn a 10 into a 5/4 or into this have to be the same number, because these two are the same number. It says so right here. So a strategy for solving an equation that isn't something we've done before, it's not what people refer to as take the log of both sides. Now, I don't know what the value of log of 5/4 is, but I could find it in a calculator. It's a decimal. I can punch a button and get a decimal value for it. This is an exact expression right now, but by the time I'm done with this, I'll be able to get a decimal approximation from what I have there. Now, how I'm going to do that, I'm using this technique to try to solve for t. The reason this is helpful is because of that exponent property with logarithms we talked about. Instead of writing 4t as an exponent, I can write it as a coefficient. So if I take the log of both sides of this expression, meaning do this, I suddenly have a new property I can use that allows me to move this exponent to a spot that's no longer an exponent. And write it as 4t times the log of 1.015. And I could take this and say, oh, this is log of 5 minus log of 4. The reason this is useful is because now t is just a number that's multiplied onto something else. This is a number. I can punch it in a calculator and get a decimal approximation of it. This is a number. 4 is a number. These are all just connected by, well, there's an equal sign there, but multiplied together. 3 numbers multiplied together over here equals 1 number over there. I can isolate the t in a way that doesn't look like this anymore, but has the same value as this. To get the t by itself here, I do log of 5/4 divided by 4 and divided by log of 1.015. And if I do this, and you can divide them one at a time on a calculator. There's a button that says log on your calculator, common log. This expression is equal to, sorry, just divided by those. That expression is equal to t. So is this. And if you can maybe see the only difference in these two expressions, the top has, instead of log of 5/4, this has log of base 1.015 of 5/4. The denominator there has two pieces, a 4 and a log of 1.015. This denominator is just a 4. So maybe you can see that this expression here, which I don't really know how to punch that in a calculator to get a decimal approximation, this part is the same as these two divided, this log divided by that log. And I just picked log 10 because it's on a calculator and I know I wanted to get a decimal answer for this. There's no specific reason I had to pick it. I could have used natural log, which is also on a calculator. I could have picked log base whatever I want. Log base 5/4. And then the numerator would be 1 over something else that I couldn't put in a calculator. But there's, like I said, there's infinitely many different ways to rewrite log expressions. Some of them are more useful than others. Some of them will help you solve equations. Some of them will just make a mess. Some of them will just make it look different if you like it to look different. But this expression here, log base 1.015 of 5/4 divided by 4, is a perfectly valid way to express this value of t. How long does it take to save up your $2,500? So is this. Log of 5/4 divided by 4 log of 1.015, which if you wanted to, you could put that 4 in as an exponent on the 1.015, which is something we could have done here. I could have worked out the 4-unit growth factor, 1.015 to the 4th, and just had an exponent of t. There's all these different ways to write equivalent expressions. They all give us the same solutions for t that sometimes look different. Decimal approximation, I honestly don't know what this is. It's probably not going to be a small number of years, like 20 years or something, because it takes a long time to earn $500 in interest on a $2,000 investment. But let's see, do I have anything I can use here? Do I have logs? Nah. Say maybe I have, oh yeah, I do. I have log base 10 and natural log, even just on this little, will it let me zoom in? No, won't let me make this any bigger. But if I wanted to evaluate log of 5/4, otherwise known as 1.25, to save myself some button pushing, that numerator is that lovely number. I need to divide it by 4. And I also need to divide it by log of 1.015. Log base 10, same log I used before. And it comes out to, I guess not too bad, 3.75 years approximately, so a little under 4 years. As the amount of time it takes to save up the money. And this goes on to show a variety of ways to solve this. I think talking about some of the same things we did, getting about 3.75. So like I said, there's a variety of ways to solve equations because there's so many properties, and don't let that be confusing. You have a lot of options as opposed, they don't contradict with one another. Some you'll just maybe find will be more helpful in certain situations than others. That's all. All right, so what I want to do now, let's see. .9 lesson, 4.9, not the lesson, the investigation. Let's see, is this what I want to look at? Yeah, so this is Mod 4 Investigation 9, which has some similar questions to the Mod 4 homework number 9 about just solving some equations. But all I want to do is just take a look at these first couple logarithmic equations here. Take a look at that A and B. See if you can write an expression that gives you an exact value of x somehow or another. There's many, many ways to do this. And then see if you can also, and maybe it involves solving it a different way, find a way to find an answer that you could punch in a calculator and get a decimal value for, and then go ahead and get that decimal value if you have a calculator on you. And then what we're going to do is look at some application problems that involve what we were doing in the first half of the chapter, write an exponential expression to model this growth and decay situation, and then answer some question that involves solving an equation, something like these. you're looking to find a way to express a solution to both of these, number one, A and B, exactly, somehow or another, lots of various ways. And then possibly solve a different way or rewrite what you have in order to make it something that you can find a decimal value for. Like a punch it in a calculator sort of expression. Not all log expressions are easy to punch in calculators. And both of the exponents in this are just plain x, and it's kind of small. You don't have your own version of it back in the back room here. Alright, what about for number one? Can anybody explain, this one's fairly small, short numbers. What would be an exact expression, there's many available, that you could use to express the value of x for number one? Anyone have one? Yeah?
Log base 4, 3 in parentheses equals x.
Almost. Got the couple of pieces in the wrong spot. Or maybe you just said it wrong. Log base, what's the base of the logarithm?
Log with a subscript 4. No.
Nope. What should be the base of a logarithm if we're rewriting this one? 3, yeah. The base of the exponent becomes the base of the logarithm in log form. So log base 3 of 4 equals x, yeah. So if I were going to estimate the value of this, what two whole numbers would it be between? Yeah, somewhere between 1 and 2, because 3 to the first power is smaller than 4. 3 squared is way bigger. Well, not way bigger, but it's certainly larger. So between 1 and 2 should be closer to 1 than to 2 as a decimal value of this. If I want to evaluate this on a calculator, anybody have an expression that is the same as log base 3 of 4 that just has not logarithm base 3 but just log or natural log that you could use to punch in a calculator? Yeah.
Would it be natural log of 3 over natural log of 4?
Almost.
Is it the other way around?
Yep.
4
The base ends up in the bottom when you're doing that. So so we had, and I apologize for some of you who are here, I'll write it, my eraser isn't very good. But if I have 3 to the x equals 4, if I take logarithms of both sides, the x and the 3 are going to be on the same side as one another. So I can take natural logs, I can take log base 10 logs, common logs, I can do whatever sort of logs I want, but those two are useful for calculator purposes. So I can have natural log of 3 to the x equals natural log of 4. And the reason doing that is useful is because of that exponent property of logarithms. It says that expression on the left I can write without an exponent. I can write it with a multiple of x instead. This is the same as x times the natural log of 3. This is log of 3, log of 3, log of 3, log of 3 added together, x times, well, I'll do x times natural log of 3. So you can see that the part that had the exponent, the base of the exponent part, to get it away from the x, I'm going to have to divide by it. So that whatever was the base of the exponent, when you do this, solving this way is going to end up in the denominator, the base of the fraction. So this expression here, or with log base 10, or log base 17, or log base 83, whatever you want, same logarithm top and bottom, with a 4 and a 3 in the numerator and denominator respectively as those arguments, should give us the result we want. Something between 1 and 2, just slightly larger than 1. And I don't know what it is off the top of my head. But again, it shouldn't matter whether you use, like for punch in a calculator purposes, you've got natural log and log base 10, or a common log. You're going to get ratios of 2 different numbers. Because in reality, natural log of 4 is what power does it take to turn an e 2.7 something into a 4? That's a weird number. What exponent does it take to turn an e into a 3? Another weird number. I don't know what either of them are. But if I do 4's natural log divided by 3's natural log, I get 1.2618. If I use common logs, let's see, 4's common log divided by 3's common log, both numbers less than 1, I get 1.2618. It's the same thing. The ratio of these exponents to turn 3's and 4's into different other numbers, I don't really care what those different other numbers are. The ratio is what's important here. Relatively speaking, how much larger an exponent does it take to make a 4 than a 3? To get the same number. So about 1.26 in this case. And you can check your answers into the original question. Now, to use this as an exponent, you'd probably round it off, like probably not 1.2618, maybe call that a 1.262 or 1.2619, since the next number is a 5, or whatever. But if you do 3 raised to that power, it should come out up to, just rounding error, approximately 4. So 1.2619, let's see if I can type on here. nope, I can't. 1.2619 to the power of, let's see, as a power on 3. Oh wait, I need to do that the other way around on this calculator. Sorry, used to other cheap calculators. 1.2619 as the exponent is approximately 4. This was rounded up. It was from that 0.5 up to the next digit. So this is slightly larger than 4, but you can check answers to these by substituting in and just by, round off error. It shouldn't be too much different as long as you've cupped a few numbers. In terms of iMath stuff, some of them will ask you to enter decimal answers. It'll say something like, don't write an expression, write a decimal answer to 5 places, because it wants to know if you actually know how to put in whatever you have into a calculator. But if it doesn't say something like that, you could write in log expressions, type in something like log of 4 divided by log of 3, and that's fine. And you'll see the decimal value calculated out to the side. In those cases where it says an expression is fine, or please enter an expression now to round a decimal, there are some of each in the upcoming homework. Now, if you compare questions A and B here, A looks much simpler, nice round numbers. B also has an extra number in a spot that A doesn't, but you can eliminate that. If you can make equation B look more like equation A, you can use the exact same set of steps, other than just, the numbers 3 and 4 aren't there anymore. You can use the same set of steps or same sets of ideas or different sets of steps to use them. So if you can see, I've got 3.4 to the x instead of 3 to the x. If I can get that exponential factors, I guess, by itself, in other words, if I can get that 17.5 out of the way somehow, I can make equation B look more like A. All I'd need to do is, one of two things. You could just divide by 17.5. That'd be the easiest way to go. If you were thinking about log properties, we could take logarithms of both sides and separate this out later, because I've got two things multiplied together here. You could take logarithms of as it is and use more log properties, but probably easiest just divide both sides of this equation by 17.5. Then I'd have 3.4 to the x equals whatever 22.4 over 17.5 is. And you can just leave it like that. You don't need to make it look pretty, like get decimals out of a fraction or anything. Because our next step would be, then do what we did here. If I want an exact expression for an answer I could write with logarithms easily, I could write log base 3.4 of 22.4 over 17.5 equals x. I could also use other logarithms, take the log of both sides, and I'd end up having log of 22.4 over 17.5 divided by log of 3.4. Common log or natural log, whichever sort of punch it in a calculator log you want to use. In terms of estimating a solution to this one, it's going to be a lot harder. But maybe you can see that if I do that division first, I'm going to have a number that's just slightly more than 1 equal to 3.4 raised to a power. If I need to turn 3.4 into something smaller using exponents, I'm going to need to do reciprocals probably. So I'm going to have negative exponents, or you should maybe expect to see actually it's larger than 1 still, so like a square root, something between a 0 and 1 sort of exponent on this one. So value of x between 0 and 1 somewhere. But in any case, other than that first step, divide by this to get it out of the way, so that this B equation looks more like the A equation. The numbers are messier, but other than that first step, you can use the same steps after that to solve. What I did want to show you, I'm going to post this whole other, you saw this briefly when I was looking for a blank document, this whole other worksheet that I have. This is something that I used in a different class. I just put our course title at the top because if you want to have some extra practice with logarithms, just quick things that would be easy to take to any tutoring center or look up solutions to online, here's a whole bunch of These say find the value of y. It's not by actually solving equations, it's by evaluating. Now, in a couple of them, the y is mixed in strange places. Write in exponential form, write in logarithmic form. Those are things we talked about last week. This is the more complex version of stuff we were talking about today. You could expand these into multiple logarithms, added and subtracted, possibly with coefficients, instead of having a single log expression with big, ugly argument things afterward. Not really concerned about that. I just, like I said, just delete that since whatever. But in terms of things I do want us to look at, I want to just talk about quickly this number 5 here. Questions 1 and 2 in particular that have a single logarithmic expression, or a single exponential expression, 3 to the x minus 2 equals 12, or 3 to the 1 minus x equals 2. Again, it's a 3, just I think because 3 is easy to type and it's not as simple as a 2. But if you want to solve either equation 1 or 2 here, get the 3 to the power by itself, and then use logarithms. Take logarithms of both sides, or rewrite in logarithmic form. So take a look at number 3. 4 to the x power equals 5 to the x plus 1. We have not seen any like that. And that just jumped. Sorry about that. There's not a way to get rid of the fact that there's 2 different numbers with exponents. Like I can't somehow make this 4 times 5 to the something power. But there are actually ways to rewrite this. Our goal, however, is to solve for x. So the equations like 1 and 2 up above are easier if you can get that 3 to the x by itself. We have expressions to x by themselves, it's just we have 2 of them. They're across equal signs from one another. It's actually okay. It makes for a little bit of a messy expression. But I can use the same idea to solve either 3 or 4. Let's just talk about 3 though. They're kind of similar. By taking the logarithm of both sides. Now, I would not suggest trying to rewrite in logarithm form log base 4 of 5 to the x plus 1 equal, that just gets confusing. But if I have 4 to a power and 5 to a slightly larger power, apparently, 1 larger, regardless of what x is, if I take logarithms of both sides, I can use that exponent property on both sides, right? X times the log of 4 is the same as x plus 1 times the log of 5. So my goal is to solve for x. There's a variety of different algebra steps I can do here. But if you imagine like log of 4 is just some number, log of 5 is just some number. In reality at this point, this is just a linear algebra equation. Like if the log wasn't there, like 4x equals x plus 1 times 5. It's like that, only it's not really 4, it's log of 4, which is some other bizarre number. It's not really 5, it's a log of 5, which is a strange number. But I've got x times some number equals x plus 1 times some other number. I should be able to get all the x's on one side and then divide by the coefficient to get x by itself, to get x equals. So despite the fact that it looks ugly, move this up a little bit, it's not under my face, I could write this side as x times the log of 5. I'm just going to leave the x's in front of the logarithm so it doesn't look like x is in the log expression. It's not log of 4x. but this is just x times a number plus some number, right? X log of 5 plus log of 5. So if you get all the x's on one side, I've got x times something minus x times something else. So I'd have x times log of 4 minus x times log of 5. And in terms of trying to solve for x, maybe you can see, oh, let me do this. That would be the same as x times log of 4 minus x times log of 5. X times the difference, log 4 minus log 5. So that's just subtracting this from both sides. And then equals log 5. So it's not a nice expression. Like if it was just the numbers 4 and 5, this would be x times negative 1 equals 5. And then I just divide by the negative 1 to get it. It's not a negative 1, it's that subtraction problem. But with one quotient and then punching in a calculator, I could get a decimal value for this, or I could just leave it as an exact log of 5 over the difference, log 4 minus log 5. And just as a note, when it is log of a single number or a numerical expression, or even if it's just an x, lots of times you won't see the parentheses written. Be very careful with that though. It's easy to accidentally combine things together, and that's another reason I put the x's in the front so it doesn't look like it's in with the 4. It's not in the log expression as an argument, it's a multiple of it. All right, in any case though, things like these, including number 4 there, you can use the same techniques with take the log of both sides in order to be able to express the answer. It just is a little bit messier algebra, but after that it really is just, after using your log properties to get the exponents out of exponent position, you have messy but just regular sort of subtract and divide algebra to take care of. All right, now, just as a just trying to decide if I want to talk about that. I just want to talk about number 7 before we leave here today. Number 7 kind of combines, and there's a number 8 also that's maybe, it's decay, but it's easier maybe. Number 7 here, bacterial culture starts with 10,000 bacteria, and that number doubles every 40 minutes. Now, usually bacteria is measured in mass because it's hard to count the individual ones, but we'll assume that they could count well, or they estimated the number based on the mass. Write a model for the number of bacteria after m minutes, and then how long will it be till there's 50,000 bacteria? So this part A would be like what we did the first half of the chapter. I should be able to write a function that models doubling every 40 minutes, and then I get to plug in a number of minutes. But that doubling, that's a 40 unit growth factor then. And so when I'm writing my equation, I want to have my 1 unit growth factor. So, this is my document here. So I can type in here. If I want to know the number of bacteria, I'll just call it f of x. Or actually, f of m, it says. So it's a formula after m minutes. Actually, I'm going to put commas in there because that looks weird. I start with 10,000, and I double every 40 minutes. Now, doubling is the 40 unit growth factor. So my 1 unit growth factor is the 40th root of that. And then if you remember doing this repeatedly in homework, if I want to know, well, how many after m minutes then, I can either use, double parentheses and then raise this to the m power, or I can just put my m right there, because I get to multiply exponents. 1/40th times m if it's a power raised to another power. So if I want to know how long until there's 50,000 bacteria, I now have an exponential equation to solve. Where much like, let's see, some of the ones we did, it's ones we did in the lesson. First step, maybe get rid of this 10,000, so I have the 2 to a power by itself, and then you can use logarithms to solve. Now the exponent isn't just an x, it's an m over 40, so once you get the exponent by itself, it'll be like a times 40 to get the m. But make sure you can still remember how to do this earlier step, and you'll see some questions like this in the homework for the 4.9. Write the function, and then use it to do something, which is why we bother writing them in the first place. But sometimes it's to, just track the amount over time, but we can also use them to solve for values over time. All right, and then the other equation in number 8, I'm gonna post this worksheet, not with that solution typed in the middle, I'm gonna post this just so you can have an example of just a whole bunch of log and exponent things together. Like I said, it was from a summer school class that I taught where we did everything but logarithms in 1 4-hour day. So we need a lot of practice. But as a kind of a wrap up to our exponential and logarithm stuff, I'm gonna post